Thank you very much for the introduction. And now I think you just revealed that I'm not a chemical engineer, so sorry about that, guys. But thank you very much for having me. Very pleased to be here and sort of happy to be able to present some of the work that we are currently doing and have started doing in sort of a very preliminary part on CFD simulations of cold gas solid flow in a pilot scale dual fluidized bed system. So I've added preliminary study because we've only been doing this for a couple of weeks, so bear with me on that. I have prepared a short presentation for today. This is the outline for the presentation, so I'll be going into some of the background and motivation for the project that I'm a part of, and some of the pilot scale facilities that we have available to the project, and then I'll be looking at some of the CFD simulations that we've done this far and currently working on, which I think you guys probably think is more interesting than the background. But in favor of the people who've been working with this project, I would just like to introduce the OxyCrack project. That is a collaboration between Catalytic and DTU, so that's the Technical University of Denmark where I study. What we're trying to do is produce a new way of producing, or sort of create a new way of producing glycoaldehyde-rich oxygenates that can then be further converted into bio-based products or materials. What that actually means in this case is that we're using a catalytic conversion technology to take sugar, put it into a cracker, as we call it, and convert it into sort of intermediate products that could be monoethylene glycol, MEG, or methyl vinyl glycolate, MVG. I think some of you might have known MEG because it's used in a bunch of, as a key component in plastic products, PET plastic bottles, polyester fibers, plastic food packaging, stuff like that. And the thing we're trying to do is to see if we can sort of replace the present way of producing these intermediate products, MEG specifically, produced from fossil-based feedstock, gas or coal, which is something that we've been doing for a lot of years, and it's quite cheap way of doing it, but it's also not a very green way of doing it. So we're trying to use this catalytic conversion technology together with circulating fluidized beds to sort of provide a cost-efficient alternative to the present way of producing these intermediate products. It's not that obvious to do, and that's why we're building some pilot scale facilities to sort of test out this technology to see whether it's viable, both in terms of, mostly in terms of money actually. So at Haldor-Topsøe at DTU, we have built 2 pilot scale systems. The one at Haldor-Topsøe, that's the one, I have laser and everything. That's the one you see here. It's quite secretive, so it's wrapped up basically. That's a hot flow system, so you have feedstock going in, evaporation, chemical reactions, everything like that. And on the right-hand side here is the the less secretive, so to speak, DTU cold flow system. So we don't have any reactions going on. We're just looking at catalyst flow, solids flow, and flow of air in the system. And the reason why we've been working on this for a couple, I'm saying we, I've not, some other people have been working on it for a couple of years. And the reason why we're spending that much money is because we're trying to build a plant by 2023 that can actually do this stuff. Hopefully in a cost-efficient way, and this pilot scale approach is sort of an intermediate step in scaling up of the technology, and also it's a lot more a lot cheaper actually to do big mistakes on these smaller systems than it is to do on the large systems. So we're trying to save money in the end. For a CFD guy like me, it's quite cool to have these pilot scale facilities just available a couple of meters from my office, because we can then do testing, we can do different operating conditions under controlled operations, and hopefully we know what's actually going on in the system so that we can try and model that and use that as a sort of validation foundation for the CFD. So looking at the cold flow setup that I have been working with and will be working with for the next time, it is sort of it's a circulating fluidized bed system, but it consists of 2 loops. So there's a reactor loop here consisting of a riser and a bubbling bed, and then there's also a regenerator loop here consisting of also a bubbling bed, a riser, and a stripper, and then we have secondary and primary cyclones on top. And then we have these transfer lines, which are sort of used to connect the two loops together. So we have a circulating flow of solids, and then we have pinch valves, basically small orifices that can be enlarged and sort of shrinked to control the solids flow rate through the system. Then we have sparges located at the bottom of the two bubbling beds. These are ring sparges to sort of fluidize the bed inventory. And we also have some simple sparges at the bottom of the reactor riser down here and below the stripper. Just to give you sort of a rough idea about what's going on in the system in terms of operation conditions, we're using catalyst particles, which when you use it or try to plug it into this Gelder chart, you end up right between A and B, which is quite annoying actually. In terms of fluidization behavior, the two bubbling beds are actually operating in bubbling mode, very close to minimum bubbling or minimum fluidization velocity. So I guess that should be more over here apparently. And the two risers are operating in sort of a fast fluidization mode. Although the superficial gas velocity in the regenerator riser is somewhat higher, so actually somewhat in, I don't know, some sort of a transport regime. But it's not really clear-cut, these lines, but it's just to give you an idea about what we're actually trying to capture, which I think is important when you want to do CFD modeling of such a system. This is a video of the operation. I'm not sure if you can actually see it this much, but this is the cold flow setup at an operation of fairly high solids flow rate. So normally in the CFD simulations we're running at 1600 kilos per hour. This is somewhat higher, but it still shows what's going on. So you have the stripper here below the regenerator bubbling bed. Then you had a fluidized transfer line going into the bottom of the reactor zone here, or the reactor riser, and then the reactor riser that goes into what's behind here actually, the reactor bubbling bed, and then into a non-aerated angle standpipe that we see here. That goes into the regenerator riser that goes back into the regenerator bubbling bed. This is a zoom in on the behavior of the fluidized the fluidized transfer line here, where we see this interesting sort of transition from a very dilute flow to a dense flow as we go above a certain solids flow rate. Of course, that's interesting to capture in the CFD, but I also think this shows just how difficult it might actually be to capture this and what's actually going on in this system. So with this system, we're actually able to conduct, or we can do pressure measurements throughout the system in terms of risers, for example, at different heights. We can do measurements of the solid circulation rate. We can do quantification of the stripper efficiency. We're also trying to implement a system so we can quantify the efficiency of the cyclones at the moment, specifically the primary cyclones. We can do radial pressurements in the bubbling beds at different heights and locations. We're also trying to use a pitot probe to see if we can measure velocities. Then we can do RTD measurements in the risers, and we're also currently working on installing optical probes to measure the solids volume fraction at different locations in the system. Okay, so going on to the CPFD simulations. So we're using, let's start over. What we're trying to do is to see if we can get a better understanding of what's actually going on in this system hydrodynamically, to begin with at least, using CFD. And we've had some experiences using Barracuda VR in our little group at DTU. So that's why we're starting using this software, and actually turns out to be quite easy to get up to speed with, and it's fairly fast, so that's why we're going down this path. Hopefully we're able to, within the couple of years, develop a CFD model to fit the experimental data of the cold flow model over a range of operating conditions, and also at some point go on to the hot flow setup. So we actually have data for the hot flow setup at the moment, but it would be nice to also have a CFD model and then use that data to sort of validate the hot flow setup. So using these two models as stepping stone, we hope to be able to predict the performance of the final full-scale plant at the end to sort of risk mitigate or mitigate the risk in going from smaller scales to large-scale systems. Yeah. So I know that the title says full loop. That's probably a bit of a stretch. So we ran into some problems fairly quickly. So what we ended up doing was actually discarding the entire, discarding the entire regenerator part of the system, so we're only modeling the reactor loop, and we're not actually modeling the loop. So we're putting in solids at a specified flow rate that we got from the experiments, together with some air, and then we're taking out the same amount of solids at the bottom of the bubbling bed. Because we weren't able to begin with at least model the pinch valves that controls the solid flow rate through the system. So that's why we're also discarding the transfer lines, at least most of them, and we're also discarding or not looking at the secondary cyclone. So we're basically just recycling all the solids that comes out directly into the bubbling bed. We're using these fluid point source injections to fluidize the bottom part of the bubbling bed and the bottom part of the reactor riser. It's very much an out-of-the-box simulation. It's sort of to get it was made sort of to give an idea about what can we do with the software, sort of what are the capabilities in terms of prediction, and especially where are the limitations in terms of modeling the system. So it's very coarse, and we're only using 260,000 cells, but it also makes us simulate 95 seconds in just about 60 hours. So I guess that's a good thing. This is an animation. It's actually 3 animations of the system during operation, or at least the simulated operation. So here the solids are colored by just a uniform color, by the particle speed, and by the volume fraction interpolated into the location of the particles in time. One of the things we tend to see is that there's sort of a buildup of particles down here at the bottom of the riser that then is flushed out, and that causes sort of a fluctuation to the amount of solid that goes through the system. But we're kind of cheating, because that would result in sort of a fluctuation in the bed height, which it actually also does, but the system mass is constant because we're pulling out the solids at a specified flow rate. So yeah, we're cheating a lot actually. We're just fitting the bed height to the experimental one, and then sort of reducing the amount of errors we have in comparing the numerical data to the experimental one. If we look closer at the riser part of the simulation, this is an animation of the volume solids volume fraction through the center line of the bottom part of the riser. What we see is we have this dense zone and a more dilute top as we we dilute the flow with this lift gas pipe here. And what we tend to see is this accumulation of particles that I talked about, just opposite of the lift gas pipe, which at some point breaks down, and then we get a sort of a transport or conveying of these particles, and that sort of causes the fluctuation. And that's something that we actually don't see in the simulation, in the experiments, and we actually had to add extra aeration in here to avoid a complete sort of accumulation of particles on the opposite side of the lift gas. Another thing that we had to do in terms of this aeration, that's the reason why we started adding the aeration, is because this, as you see, is a lot more dilute than what we saw from the video in the transfer line. We did have some problems with mass deficit on the inlet boundary condition here. So what we did instead was just add a bit more aeration to get a sort of a stable flow of solids through the inlet. The stacking of these particles also causes sort of a skewed velocity profile in the bottom part of the riser that results in a skewed solids concentration profile. But as we go further up into the riser, we luckily get this sort of core annulus profile that we would expect for this type of riser. What we don't see actually is downward flow of solids near the riser walls, which we would expect, and we also see that in the experiments. We're using a homogeneous gas ball model, and there have been some studies in terms of Geldert B, A, especially B materials, that might suggest that if you had a heterogeneous model, that would actually capture this trend. So that's some of the next steps we're working on. If we look in terms of some more quantitative data, then we've been looking at just pressure distributions across the system. I'm only going to talk about the riser because I don't have time to go into details with the bubbling bed. But if we look at the pressure, we are measuring it at 7 different locations across the height. So it's about, I didn't mention that, but it's 4.5 meters tall, and it has a diameter of 60 millimeters, so it's quite small in diameter. And we're measuring at 7 different locations, and they're close to the wall, and we're doing the same thing in the CPFD simulations to sort of have a one-to-one comparison. What we tend to see in terms of absolute pressures is that we get a very shifted profile to the left. Some of it is due to the fact that the pressure drop at the bottom of the riser is overestimated due to this accumulation of particles that increases the pressure drop at the bottom. We also have some problems with the outlet conditions. So at the moment we're specifying an outlet pressure at the top of the primary cyclone. We don't actually know what that pressure is, unfortunately, so we had to estimate it. And that sort of also conditions or sets a sort of a ground level for what is the pressure at the top of the riser. So there's some sensitivity to the outlet pressure at the cyclone. But if we sort of normalize that and take a gauge pressure relative to the pressure at the top of the probe 7 here, then we get something that is a bit, well, it looks a lot neater at least. So we're capturing some of the trends. Of course, there's still some problems with the bottom part here. One of the big problems we have in this is you see the difference in standard deviations on the numerical data versus the experimental data. So we're only averaging over 50 seconds compared to 371 seconds for the experiments, and that causes this relatively high standard deviation. So we have to do some more on basically just simulating for a longer time, I think would solve some of that. But if we look in terms of overall pressure drop across the height of the riser, then we're doing a fairly okay job in predicting that, even though we're seeing some trend problems. And also in terms of the bubbling bed, we're doing a fairly okay job. We are cheating in this case because we're fixing the bed height to the experimental one, so I guess this is to be expected. The last couple of minutes, I just wanted to talk about some of the challenges and also some of the good things that we've seen in using the Barracuda software. So of course, in setting up such a model, there are, when just doing CFD, you have to think about what is the system that you're simulating, and that's sort of on our side. But when using a specific software, you then have challenges, but also pros and cons in setting up the same boundary conditions and models there. So I'm going to talk a bit about both. So in terms of just setting up the system, first thing you need to know is how are your boundary conditions and how do you define your boundary conditions at the points where you actually sort of disconnect your system and define your boundaries for your fluid domain. And we have sort of had an ongoing discussion on the points where, so we're cutting off parts of the system, which makes sort of an artificial boundary right there. So how do you obtain proper boundary conditions at these locations? How do you get those from experiments? But also once you have them, how do you actually implement them in the software to get sort of a physical representation of what's going on? And I think the fact that we had to add extra iteration to the transfer line says something about the difficulty in just going from knowing the boundary condition to actually implementing it in a proper way. Then we had this problem at the pinch valves that we weren't able to model, at least not to begin with, that I'll be talking about in a bit. And that also causes us to sort of disconnect the system into two, and then we get these additional boundaries that we don't actually want because that puts extra sort of inaccuracies to our modeling. And then we have this entire ongoing discussion about drag models that have been discussed a lot here, but not as much as drag models as general validation as such, because the question is, how do you validate a CFD model? That's actually a good question. How much data do you need to validate a CFD model? Which type of data? And when do you say this is validated? So there's something about what data to collect, but then there's also the question of when do you start tuning your model, and when do you say, okay, my boundary conditions are flawed, so that's where I start. So in this case, we've just assumed that all our boundary conditions are rubbish, so we use an out-of-the-box simulation approach instead. But there's this ongoing discussion on when do we actually start tuning, when do you select a different model, and there are different ways of handling that. The reason why we're not doing this pinch valve, or including the pinch valve at the moment, is due to the fact that we're having some troubles in resolving, as I think it was mentioned before as well, complex geometries, but also just simple, small geometries, internal geometries. So vortex finders with a small sort of thickness in large vessels, they're quite difficult to capture using the current meshing tool, but it's quite easy to run. As it was also said before, we don't have any problems in terms of convergence. You might find that when you're doing chemical reactions, but this is actually, it's quite easy to set up. It runs very fast, and it's easy to get up to speed with. Then we have this, I don't think it has been mentioned actually, but we use these fluid point source injections to simulate the spargers, which is quite nice actually. because we get a better representation than just having a uniform boundary condition at this point. But because we're not able to have these sort of local mesh refinements, we can actually resolve the gradients of the fluid flow, which for a mechanical engineer is something that you're going to be like, what is going on? But so you get the proper mass flow rate, but you're not going to get the jet velocities correctly, which I tend to guess that will have an effect on the near region fluidization behaviors, which in the conditioning zone, as we just saw for the riser, that might be a problem. In the moment we're using an LES model, it would also be nice to have the opportunity to select some of the more traditional turbulence models, K epsilon, K omega, at least for the dilute areas. I guess that you guys are not fond of that for the more dense regimes, but it would be nice. And also, I think it's actually in there in the beta version at the moment, a model for turbulent dispersion of particles, which we expect would have some sort of effect at least, but it's not really documented. It would be nice to see what the effects of that are at the moment. So with that, I think I'd just like to conclude. I've spent a bit more time than I was supposed to, sorry. So we're trying to use Barracuda, a virtual reactor, to simulate this full loop pilot scale version, first of all in cold flow, and then secondly, hopefully in hot flow conditions. We've done a preliminary study just to identify the challenges and some of the good things in using the Barracuda software, and we actually found that using this out-of-the-box simulation is fairly easy, very easy to set up, and we actually get some fairly acceptable predictions in terms of overall trends and specifically pressure drops. We do have this problem of the pinch valves that sort of disconnects the system, so we can't at the moment have a proper full loop simulation going. So that's something that we'll have to work on, and also try basically just to improve the accuracy of the model through appropriate drag model selection, the necessary sensitivity studies that we haven't been conducting yet, and then improving our boundary conditions. So I'd just like briefly to say thank you to the Innovation Fund Denmark for paying me, and Technical University of Denmark supervisory teams, as well as the ones from Helder Topsøe from helping out with the problem, or with the project. So thank you very much.
Yeah, getting paid is important.
Yeah,
so.
Yeah, definitely. That's why I'm here.
No, I don't think everybody realizes how use the term out of the box, but also hot off the press this is. I think we exchanged emails last week about, can I let it run over the weekend to have some newer results? So what you're seeing is, I think, a first pass, taking one component of it, and then the normal questions that you're asking, really good questions on what boundary conditions do I use, and then when do I make sure it matches the real system, and when do I calibrate? So I think you're on the right track. Let's open this up to maybe just one question, and we're going to have to move on. We have one more talk then before lunch. Lev, if we could just hang on just a second till we get that microphone.
Okay, so, sorry. You showed profiles at different elevations in the riser, right? In the vaporizer, at the wall, you have close packing. Solid volume fraction at the wall around 0.6 or so. Do you believe that? Have you tried to compare with literature data? Because I think at your scale you may find some.
And I was going to ask the same thing. I think you actually have a different scale as you go up.
So yeah, it's quite difficult. It's quite difficult to capture the entire range of this here. So yeah, maybe I should have said that. But I'm modeling or modifying the range here. So that red, sorry, that red is not the same as that red over there.
Okay, because that kind of contradicted you saying, okay, the drag law, the drag's actually too strong, right? You were saying that Gibbs drag may not be the best choice here, but with 0.03 at the wall, yeah, that's believable with conventional unmodified drag law. Okay. Thanks.
Yeah, sorry about that.
The same thing.
Yeah, sorry.
Thank our speaker one more time.